Welcome to Modulus Water. Current desalination plants are massive and costly infrastructure facilities that consume enormous amounts of energy. The world is changing, though. Over the past decade, the cost of generating renewable power has plummeted by more than 90%. But the soaring costs of battery storage and long-distance transmission limit the widespread adoption of these power sources. Today, electricity demand is growing faster than the world's population, driven by public resistance to fossil fuels and by new loads from AI-driven data centers and electric vehicles. The grid of the 20th century is struggling to adapt to the demands of the 21st. So we asked, what if we could create a mobile desalination system that runs exclusively on renewable power, independent of a stable grid, allowing it to operate anywhere feed water is available? Such a system would need to provide potable or irrigation water, on demand, at a cost comparable to alternatives. If we produced water when renewable power is available, we could store water instead of electrons, dramatically reducing production costs while removing dependence on a modern electrical grid. The components of this approach are all available commercially, but we would need to put them together in an unconventional way. As a first test, we created a digital twin of a commercial reverse osmosis system. This software approach was designed to simulate its responses to intermittent solar and wind power, with only short-term battery storage. This model enforces all physical constraints: fouling, battery charging, pressure requirements, and salt rejection physics. We then chose a suitable test site to simulate a renewable power generation profile, focusing on the nearshore Persian Gulf, a region where desalination is essential. Using 2022 weather data for this site, we trained an AI model to maximize water production, accounting for the realistic uncertainties in noisy sensors and imprecise weather forecasts. In the real world, such an AI model would need to allocate power between use and storage with minimal curtailment. When tested on 2023 data, we found that AI control accurately distributes available energy between water production and storage, producing 95% of the maximum calculated with perfect knowledge. Even though our system lacks a pressure exchange energy recovery system, we calculated overall efficiencies between 6 and 7 kilowatt-hours per cubic meter, despite operating under variable power. To see if this simulation was accurate in the context of the X-Prize competition, we chose a 2-week power profile to test our hypothesis. We retrofit a commercial system with a variable power controller, not only to validate the model, but also to determine whether productivity and quality can be maintained. The testbed exceeded expectations, providing significantly more than 1 cubic meter per day productivity during the 2-week test period, creating water at 10 kilowatt-hours per cubic meter despite intermittent variable power. Local testing of the permeate near the end of the test period revealed no observable loss in productivity or quality. The success of these tests paves the way for a pilot-scale, containerized modular system for field testing under real-world conditions. For Phase 1 testing, our prototype system demonstrated over 100 hours of intermittent operation across a 14-day period, producing more than 14,000 liters of potable water. In Phase 2, we will show that this approach is practical in the field with more advanced hardware, including an energy recovery pressure exchanger, while using the same AI control architecture operating with real seawater and real renewables. And in Phase 3, we will create a market-ready mobile and fully renewable desalination system. Our approach is fully scalable and can be adapted to variable circumstances where fresh water is needed. To summarize the progress to date, we have shown that commercial off-the-shelf hardware can operate effectively in an intermittent power environment, using variable recovery that adapts to power availability. Our proprietary AI software provides robust, executable control decisions despite real-world variability. We have modeled designs for both the pilot and final stage systems using our physics-based digital twin. Based on commercially available components, we can construct scalable systems capable of at least 1,000 cubic meters daily, prepared for immediate deployment.